We're starting today's session with section 3.3, where we're going to extend what's been said so far in relation to multiple regression models to include the books referring to it as other considerations. The first one would appear to be when working with data that isn't necessarily numerical, but we have qualitative predictors. Let's start reading. In our discussion so far, we have assumed that all variables in our linear regression model are quantitative, so that means numerical, but in practice, this is not necessarily the case. Often, some predictors are qualitative. For example, the credit dataset displayed in figure 3.6, and we have a nice summary over here. So how does this work? Let's add a couple of colors over here. So for instance, you could take age. Age would be numerical. Although if you're looking at it to the nearest whole number, so for example, the person's age on their last birthday, on their most recent birthday, that's kind of qualitative as well. Well, maybe not. Maybe that's going a step too far, but it wouldn't be continuous. It would be numerical but discrete. So it's going up in steps of 1, for instance. Or this discrete could also be going up in steps of 0.1 or 0.01. The opposite of discrete is continuous, where you can, at least between your minimum and your maximum, have theoretically any observation with a numerical value between that minimum and maximum. Now, each of these charts is plotting. You can kind of think of it as sort of like in simple linear regression, where we have one variable against another. So education would probably be qualitative, and this is plotting education against limit. This would probably be like a borrowing limit. In fact, can we see if the data is available in R? Is it in the ISLR package? ISLR, and if we do data, credit, yeah. So here we go. Let's take just the first few records, take the first 2. And it's exactly well, or is it? We have income, limit, rating, cards, age, education. There's also gender, student, married, ethnicity, and balance. Rating would be your credit score. I think it works. The higher your rating, then that's an indication of how good a borrower banks might consider you. How good of a borrower, how likely is it that you're going to make your payments, you're going to make them on time, you're not going to default, and you're going to, over the lifetime of the loan, you're going to pay the loan together with any associated interest. So this is some of them, not all of them, right? There isn't student, for example. let's have a look. So we record balance. That's the average credit card debt for a number of individuals, as well as several quantitative predictors. We have age, cards, that would be the number of credit cards, education, that's years of education, so that's also quantitative, income, limit, rating. So in fact, these are, I think the ones that we've taken over here, they are all quantitative. For those of you just joining, we're looking at the credit data set in the ISLR package. We have 400 observations, 12 variables, so 12 fields for each record. We have a unique ID from 1 to 400, income, limit, rating, cards, age, education, gender, student, married, ethnicity, and balance. So this is the first time in this chapter that we are looking at data that isn't wholly numerical. It isn't quantitative. Another way of getting an idea of what's going on in a data set is the STR function. Think of it as the structure function. And in fact, these variables over here, they are qualitative. And R is telling you these four, they are a factor type data, where gender is in 2 levels, male, female. We have student is 2 levels as well. You either are or you're not. Married, yes, no. And there are 3 types of ethnicities. So this is qualitative data. Each panel of figure 3.6 is a scatter plot for a pair of variables whose identities are given by corresponding row and column labels. For example, the scatter plot directly to the right of the word balance, so we're looking at this one, depicts balance versus age, while the plot directly to the right of age corresponds to age versus cards. In addition to these quantitative variables, we also have 4 qualitative variables. So these are the ones that we just saw in R. Gender, student, so that's your student status, yes or no. Status, which refers to marital status, and ethnicity, we're dividing into, you can, each observation has to be one of these 3 types of ethnicities: Caucasian, African American, or Asian. And are we performing linear regression over here? Although instead of taking maybe all the genders, are we looking at only the females? Let's see. Least squares coefficient estimates associated with the regression of balance onto gender in the credit data set. The linear model is given in 3.27, so this is when we continue reading on. That is, gender is encoded as a dummy variable, as in 3.26. So let's have a look. Predictors with only 2 levels. Suppose that we wish to investigate differences in credit card balance between males and females, ignoring the other variables for the moment. If a qualitative predictor also known as a factor, which is what we saw in R, right? So if it's a qualitative predictor, if it's non-numerical, we will see that R itself refers to this type of data, not as an integer, not as numerical, but as factor type. Only has two levels or possible values, then incorporating it into a regression model would appear to be very simple. Let's see. We simply create an indicator or dummy variable that takes on two possible numerical values. For example, based on the gender variable, we can create a new variable that takes the form xi is 1 if the ith person is female, is 0 if the ith person is male. And use this variable as a predictor in the regression equation. This results in the following model. Let's have a look. Let's have a look. So it's simple linear regression. We're taking, for example, balance and regressing it on the gender. But if it's qualitative and if it's only two levels, xi is either 1 or 0, meaning this green expression simplifies to this if the observation is a female observation, and to this if the ith person is male. Now, beta naught, I see. Look at this, look at this. Let's find my cursor. Beta naught can be interpreted as the average credit card balance among males, right? What is the average of the error term? The average of the error term, at least in what we've been doing in this chapter, is 0. The mean, I mean, should we use the word average? Strictly speaking, it's the mean. The other types of averages. So beta naught is the average credit card balance among males. Beta naught plus beta 1, and of course beta 1 may very well be negative, as the average credit card balance among females, and beta 1 as the average difference in credit card balance between females and males. So if you estimate beta 1, one interpretation is that beta 1 is the average credit card balance difference between your males and females. Figure 3.7, or table 3.7, shall we try doing it in R? How would this work? So you want to take credit balance, okay, and just call this your Y data. Your X data is credit gender, and we can create a linear model where the formula is Y data regressing on, did I even have to do it this way? Probably not. I think these two lines were kind of extra. I could have typed it in a different way. And the data is just credit. Actually, this may very well not even work. No, it works. And we have the same two values as in the book, 509 and 19.73. Can I, if I delete everything and just start it from the beginning? Just like to see if there was an easier way of doing it. So we need to get the ISLR library. That's not going to work. The ISLR library. We call the data credit. Call it as in we extract it from the package. And can we just create the linear model? All we would say is, what's the formula? Do I even need to type credit? Can I just do it this way? I'd actually be surprised if this works. But it does. It does. I think the fact that you're saying data credit, then without having fixed or attached this data set, or knows to look for balance and gender within the credit object. Let's say, I don't know, my model, and we save it as an object to get the summary. So now we can get all these diagnostics, which are these over here. And we've been discussing t-values quite a bit these last few times that we've met. And the t-values are there to test the hypothesis that there is no relationship between, in this case, balance against gender. And a memorable way of memorizing how to interpret the p-value is, if p is low, h naught must go. And p is not low over here. What do we mean by low? Well, it depends on which significance level, which level of significance we've decided prior to the experiment to operate on. And this number, it's roughly 70%. It's none of these significances, right? It's not less than 1%, it's not less than 5%, it's not less than 10%. In fact, it's this one. It's closer to 1 than any of the other probabilities over here, which is exactly what we have in the table. Table 3.7 displays the coefficient estimates and other information associated with the model. The average credit card debt for males is estimated to be $509.8, whereas, females are estimated to carry 19.73 in additional debt for a total of 529. One thing we should have done at the very beginning was a scatter plot. You need to start from the x-axis when you're doing plots. So but would this even work because it's qualitative data? Okay. So if it's qualitative data, what it does is it doesn't plot the specific data points. instead it just gives you a box plot for the males and a box plot for the females. Okay. However, we notice that the p-value for the dummy variable is very high. This indicates that there is no statistical evidence of a difference in average credit card balance between the genders. So although the model does give you 19.73 as the average difference between the group of males in our data set and the females, the p-value isn't low enough for us to reject the null hypothesis. And in fact, we actually say that the $19.73 is not statistically significant. The decision to code females as 1 and males as 0 in 3.27 is arbitrary and has no effect on the regression fit, but does alter the interpretation of the coefficients. If we had coded males as 1 and females as 0, then the estimates for beta 0 and beta 1 would have been 5 to 9.53 and negative 19.73. If you add these two values again, you retrieve the 509 that we had earlier. Alternatively, instead of a 0-1 coding scheme, we could create a dummy variable, 1 and negative 1. In this case, for the women, you would get this expression. For the males, you would get this expression. And what do we need to do this time around to interpret if we, if you subtract these two, the beta naughts zeroize, and you get 2 beta 1, although that doesn't seem to be very important. Let's continue reading. Now, beta naught can be interpreted as the overall average credit card balance, ignoring the gender effect. And beta 1 is the amount that females are above the average and males are below the average. Okay. In this example, the estimate for beta naught, would be $519, halfway between the male and female averages of 509 and 529. The estimate for beta 1 would be 9.865. Yeah, which is half. That's what I meant with if you subtract, you get 2 beta 1. So subject to the formula, beta 1 is half the average difference between women and men. It is important to note that the final predictions for the credit balances of males and females will be identical regardless of the coding scheme used. This is what we mean by a dummy variable, that I guess you have a choice. You could label them 0, 1, or 1, negative 1. I'm sure there are many other ways of coding the data. Remember, this is when you're working with qualitative data, you kind of want to make it look numerical. The only difference is in the way that the coefficients are interpreted. So what's interesting to note is that by default, I think the coding, so I wonder if this is the coding that we're using in R, 1 for male and 2 for females. It does make a difference, like what we just read. Now, what if we have more than 2 levels when a qualitative predictor has more than 2 levels, a single dummy variable cannot represent all possible values. In this situation, we can create additional dummy variables. For example, for the ethnicity variable, we create 2 dummy variables. Let's have a look. So the first one, I see. So what you're going to do is, you're actually going to have 2 variables. There's going to be 2 of them. There's going to be one asking Asian, not Asian. And the other one asking Caucasian, not Caucasian. Now why are 2 enough? It's actually quite easy. Number one, you can never have both of them equal to 1, because we're assuming that you can only be either Asian. You can't be both Asian and Caucasian, so they can never both be 1. They can never both be 1. If this is a 1, then this has to be a 0. If this is a 1, this has to be a 0. Or else both of them are 0. Now, if both of them are 0, just because we're using a variable with 3 possible, we shouldn't call them values, right? They're not numbers. Let's call them levels, which is in fact what the book is using. If they're both 0, then you would say, okay, then I'm looking at an observation that is not Asian. I also know that the observation is not Caucasian. And since it's 3 levels, then you have to conclude, well, then this observation has to be, I think it would be African American, right, in this case. Then both of these variables can be used in the regression equation. So now it's going to become a multiple linear regression model. And we're regressing yi on these 2 variables. And you have, like I just said, there are 3 different types of scenarios. There is when this is 0 and this is 1. In that case, the person is Asian. When this is 0, in fact, beta 1 does not appear, and this is 1, that's Caucasian. And when they are both 0, that would imply that the person is African American. Now, beta naught can be interpreted as the average credit card balance for African Americans, beta 1 as the difference in the average balance between the Asian and African American categories, and beta 2 can be interpreted as the difference in the average balance between the Caucasian and African American categories. And how do we actually do this? Is it taken care of in R? If we replace balance with, if we replace gender, right? If we replace the 2-level gender variable with the 3-level ethnicity, it seems to be doing something. Let's see. Do we have 531, negative 18.69, and negative 12.50? Yeah. So it's the same values. Again, these don't appear to be significant. let's see. There will always be one fewer dummy variable than the number of levels. The level with no dummy variable, African American in this example, is known as the baseline. Quite an important concept. From table 3.8, we see that the estimated balance for the baseline, so African American, is $531. It is estimated that the Asian category will have 18.69 less debt. Oh, so balance is what's left of what you owe the bank or whatever type of lending institution we've taken this data from. So $18.69 less debt than the African American category, and that the Caucasian category will have $12.50 less debt than the African American category. However, a bit of deja vu over here, the p-values associated with the coefficient estimates for the two dummy variables are very large, 77%, 82%. Look what a large standard error it is. What do we mean by large? Relative to your estimator. Suggesting no statistical evidence of a real difference in credit card balance between the ethnicities. Once again, the level selected at the baseline category is arbitrary, and the final predictions for each group will be the same regardless of this choice. So what's interesting is, would you know from advance? Would you know in advance, is what I mean, which level is going to be selected as the baseline level? Does it have to do maybe with just the, yeah, it might be related to how these appear, perhaps. So whichever one, I'm guessing, of course. I don't know. I don't know how it works. But R must have some kind of default setting that it's always going to pick. Maybe it depends on the most commonly occurring, or just in which order the different levels occur in the data. But one of them needs to be selected as the baseline. However, the coefficients and their p-values do depend on the choice of dummy variable coding, rather than rely on the individual coefficients. We use an F-test to test the null hypothesis that both parameters are, that the true value of both parameters is 0. This does not depend on the coding. The F-test has a p-value of 0.96. Here we go, look. The F-test has a p-value of 0.96. It's practically 1, indicating that we, that we cannot reject the null. Oh yeah, exactly. When p is low, then h naught must go. P is certainly not low, it's nearly 100%. So what do you conclude? We cannot reject the null hypothesis that there is no relationship between balance and ethnicity. Using this dummy variable approach presents no difficulties when incorporating both quantitative and qualitative predictors, for example, to regress balance on both a quantitative variable, such as income, and a qualitative variable, such as student. We must simply create a dummy variable for student and then fit a multiple regression model using income and the dummy variable as predictors for credit card balance. There are many ways of coding qualitative variables besides the dummy variable approach taken here. All of these approaches lead to equivalent model fits, but the coefficients are different and have different interpretations and are designed to measure particular contrasts. This topic is beyond the scope of the book, and so we will not pursue it further. Let's move on to 3.32. Extensions of the linear model. I would imagine this is where we're going to try allowing for nonlinear effects. The standard linear regression model, that's 3.19. What was 3.19? We're looking at this, right? This is the most general form. It includes, as a special case, simple linear regression, where your parameters only arrive till x1. You only have one predictor variable. I should have said your parameters are beta naught till beta 1. And of course, you have your error term. Okay, so that's the algebraic formulation. It provides interpretable results and works quite well on many real-world problems. However, it makes several highly restrictive assumptions that are often violated in practice. I mean, if only things were linear. Two of the most important assumptions state that the relationship between the predictors and response are additive and linear. What do we mean by additive? Let's see. Additive means that the effect of changes in a predictor xj on the response y is independent of the values of the other predictors. Okay, so this is, I guess, when you don't allow for interaction. The linear assumption states that the change in the response y due to a 1-unit change in xj is constant, regardless of the value of xj. It doesn't, you know, that very often breaks down very quickly. In this book, we examine a number of sophisticated methods that relax these two assumptions. I would imagine we're going to have entire chapters on the types of approaches that we may take to sort of refine a model that may start out life as linear to reflect any nonlinearity, any statistically significant nonlinearity, right? Here we briefly examine some common classical approaches for extending the linear model, removing the additive assumption. In our previous analysis of the advertising data, we concluded that both TV and radio seem to be associated with sales. The linear models that formed the basis for this conclusion assume that the effect on sales of increasing one advertising medium is independent of the amount spent on the other media. Whereas in fact, very often they influence each other, right? For example, the linear model 3.20 states that the average effect on sales of a 1 unit increase in TV advertising is always beta 1, regardless of the amount spent on radio. However, this simple model may be incorrect. Suppose that spending money on radio advertising actually increases the effectiveness of TV advertising, so that the slope term for TV should increase as radio increases. In this situation, given a fixed budget of 100K, spending half on radio and half on TV may increase sales more than allocating the entire amount to either TV or to radio. In marketing, this is known as a synergy effect, and in statistics, it is referred to as an interaction effect. For example, think of, I don't know, you're doing your actuarial exams, and in one session, you plan on sitting 2 exams that are closely related. So studying 1 hour for exam A and 1 hour for exam B, you get this interaction effect where studying for A helps for B, and maybe studying for B also helps for A. This is what we mean by interaction. Figure 3.5, let's see. Where is figure? This is figure 3.5. This is figure 3.5. I mean, looking at it, I wouldn't have really thought of interaction. Let's see. Figure 3.5 suggests that such an effect may be present in the advertising data. Okay. Notice that when levels of either TV advertising or radio advertising are low, then the true sales are lower than predicted by the linear model. But when advertising is split between the two media, then the model tends to underestimate sales. So you're underestimating the sales when kind of your advertising budget is split between TV and radio. Oops. Consider the standard linear regression model with 2 variables. This over here. According to this model, if we increase x1 by 1 unit, then y will increase by an average of beta 1 units. Notice that the presence of x2 does not alter this statement. That is, regardless of the value of x2, a 1 unit increase in x1 will lead to a beta 1 unit increase in y. One way of extending this model to allow for interaction effects is to include a third predictor called an interaction term, which is constructed by computing the product of x1 and x2. So let's see. We're going to include this term over here. Now, how does that help? So your beta 3 is giving you an idea yeah, so the contribution of the pink to the y depends on x1 and x2. How does inclusion of this interaction term relax the additive assumption? Well, first of all, we do a bit of algebra on, let's see if we can follow without typing anything. Seem to be doing algebra on these two terms. We've taken x1 out as a common factor. And then you take all this as a new parameter. Take it as tilde beta 1. Huh. Okay. So it's going to depend on x2. So now we're saying where beta 1 tilde is beta 1 plus beta 3 x2. Since beta 1 changes with x2, the effect of x1 on y is no longer constant. Adjusting x2 will change the impact of x1 on y. Pretty cool, right? So we have this interaction term. That means that we now can't say increasing TV budget by, what would that work out to? This is in thousands of dollars, right? So 1, 2, 3. Is that $9 if I multiply by 1,000? So now I can't simply say increasing the TV budget by $9 is going to increase my sales by 1 unit of sale, because TV doesn't just appear here, but it appears over here as well. Adjusting x2 will change the impact of x1 on y. Are we going to use a different type of data set? We have lines and workers. For example, suppose that we are interested in studying the productivity of a factory. We wish to predict the number of units produced on the basis of the number of production lines and the total number of workers. It seems likely that the effect of increasing the number of production lines will depend on the number of workers, since if no workers are available to operate the lines, then increasing the number of lines will not increase production. This suggests that it would be appropriate to include an interaction term between lines and workers in a linear model to predict units. Suppose that when we fit the model, we obtain. Okay, so all these numbers are estimated parameters, and we have this first line. We have this first line where we've estimated the 4 parameters: slope, the parameter for the number of lines of production, the parameter for the number of workers, and the parameter for lines interacting with workers. You can then just do a bit of algebra and obtain this term, which now means adding an additional line this, adding an additional line, will increase the number of units produced by, not by a constant, but by this. Hence, the more workers we have, the stronger will be the effect of lines. Okay, now we're going to return to the advertising data. A linear model that uses radio, TV, and an interaction between the two to predict sales takes the form this, but then you group the TV term with the radio times TV term. So it's, you can still think of it, although strictly speaking, we have three predictor variables, TV, radio, and the third variable is radio interacting with TV. You can sort of rearrange things this way. We can interpret beta 3 as the increase in the effectiveness of TV advertising for a 1 unit increase in radio advertising, or vice versa. Yeah, I think vice versa, I don't know, to me it makes a bit more sense. The coefficients that result from fitting the model 3.33 are given in table 3.9 over here. And look, they are statistically significant. We could maybe conclude over here and we'll continue. It's actually going on for a lot longer than I expected. We then have nonlinear relationships, and then a couple of problems, a couple of like challenges. This is where you transform your data to make it more linear. You take log, square root, or square. But I think this is still quite a few pages to cover. We should be finishing this chapter. I think by next week we'll finish it. But this is where we're going to stop today.